Entropy. You would have heard this term entropy when you were learning about thermodynamics in your school. In thermodynamics, entropy is a measure of disorder or randomness. So the term entropy, it originates from thermodynamics only, where it is used to measure disorder or randomness. Coming to machine learning, what is entropy? Machine learning, or in information theory, what is entropy? It is a measure of uncertainty or surprise that is associated with a random variable. Okay, so this is defined as the average amount of information that is produced by a random event. Let us say some event happened, then what is the average amount of information that is produced by this random event? So in machine learning, we need it in order to measure uncertainty or surprise. So why is it so? Because let us consider some discrete random variable. Let us say you have a discrete random variable x, and let us say this x can take many values, and let's say small x is one value. When it takes this value small x, how much information is received when we observe this specific value of x? This is what is information. That is, how much information did you receive when you observed this specific value of x? And the point is, when the amount of information increases, there is a higher degree of surprise, or let us say there is lesser probability. Why is it so? Because let us say there is some event whose probability is very less. That is, it is a highly improbable event or a highly unpredictable event. In this case, according to you, this event is not even supposed to happen. According to you, it is a very impossible event. But you are told that it happened. In that case, you got a lot of information because you were never expecting this thing to happen. According to you, this won't happen. But you got to know that this happened. This is a very highly improbable event. When this happened, you got a lot of information from it. In other words, the entropy of this event is very high. Entropy is high, right? Let us consider some other event. Let's say a certain event. Let us say I'm telling you that I tossed a coin and I got heads or tails. So you already know that if you toss a coin, you'll get heads or tails only. There is no other option. So this is kind of a certain event. So associated with a certain event, there is no information for you to get because you already know this is what is supposed to happen. So the information content is very low associated with this event. So let us understand this with an example. Let us say I'm telling you that when I traveled in train today, when I was traveling, the train was going on at 100 kilometers per hour. Okay, I'm telling you that train was traveling at 100 kilometers per hour. What are you feeling when you heard the statement? You would have felt like, what is so special in this, right? Because according to you, it is a very normal thing that a train can go at 100 kilometers per hour. There is nothing special in it. And because of that, when I told you that the train was going at 100 kilometers per hour, it didn't add any information in your mind. The information content is very less, which means entropy is less for this particular event. Instead, what if I told you that the train was traveling at 1000 kilometers per hour? If this is what I told you, this time you are surprised because you never expected that a train could go at 1000 kilometers per hour. Now, if I'm telling you that when I was coming today, it was at 1000 kilometers per hour, this thing has a lot of information in it because this is something you never knew. You never expected this to happen. So this is an event of very less probability, and very high entropy, right? So this is the case, and let us consider an event x, and let us say P of x is the probability. P of x is the probability of that event. In that case, h of x, let us say, is a monotonic function of this probability P of x. And we will consider this h of x as the information content. That is, this is a monotonic function of probability which would depict the information content. In this case, what will happen if there are two independent events x and y? Let us say there are x and y, two independent events. In that case, probability, we already talked about probability in previous lectures. if x and y are independent, then p of xy, that is the probability of x and y happening together, is probability of x into probability of y. This is in case of probability. So when you multiply probabilities, it actually decreases because both the values are lesser than 1. But what in case of information h of xy? We will get into entropy. In information, because these two events are independent and I'm telling you both of these events happened. So you got the information regarding first event, then you got the information regarding second event. Now what is the total information? It is the sum of both those, because information can only add up. I'm telling you, I'm giving you some information I1, then I'm giving you some other information I2. So total information you have is I1 plus I2. You have total knowledge now. Same thing here. H of xy equal to h of x plus h of y. Here, if something has a low probability, then the information should be higher. And in this case, how would you define h of x, and what will be the formula for h of x? Okay, h of x is the information associated with this event. So h of x is minus log to the base 2 p of x. Here base, we will discuss about the base. As of now, let us say base is 2 for the log, that is this base, minus log p of x. I'm telling you, this value is always positive. It is always greater than or equal to 0. Always it is a positive value. How can it be always positive? Because probability, you know, p of x is always in the range 0 to 1, right? Probability is always in the range 0 to 1. Log of a number n, which is in the range 0 to 1, would be negative. That is, this log p of x term, this will be negative. So negative of a negative term will be positive, which means h of x is always a positive quantity. Moreover, as p of x decreases, h of x would increase. That is the concept. Let us get into what is entropy. So consider there is a sender and a receiver. Okay, the sender is transmitting some information to this receiver. So as the sender transmits the value of, let's say, some random variable to the receiver, the average amount of information that is transmitted, that is what you call as entropy. Average amount of information that is transmitted is called entropy. So whenever I say average, it is in the sense of expectation. So the expectation of information h of x, expectation of this is what you call as entropy. And in our previous lectures, we did see how expectation is to be found. So expectation is denoted by capital H in this particular case, because it is expectation of this particular information h of x. Let's say expectation of h of x, that is, this is the expectation of this information h of x. How do you normally define expectation? You have to sum over all the terms, right? X into probability of x. This is how you normally find expectation. Here what is x? X is this term, information, minus log to the base 2 p of x, and probability of x would remain as probability of x. That is, while you are summing or integrating whatever, in case of continuous random variable you integrate, in case of discrete random variables you take sum. You have to sum the value into the probability of that occurrence. That is, what is the probability of occurrence of this? That is p of x. So you have to sum over all the values of x, right? Probability of x occurring, p of x, into what is the value of information, that is minus log to the base 2 p of x. I'll put minus here, minus log to the base 2 p of x. This is what is your entropy. Okay, I'm removing this off. So entropy is the average amount of information that is transmitted when you transmitted a random variable from some sender to a receiver. So let us understand this. So I told you this is average amount of information, entropy, and another way of understanding this, or another perspective about entropy, is that it is the minimum number of bits that are required in order to transmit this message. Minimum number of bits that are required to transmit, let's say, some random variable. Let us take an example and understand this, then it will be easier. So I'm telling you that there is some random variable, some random variable which is, let's say, x, which can take 8 different values. Let the 8 different values be x1, x2 and so on. Let's say x1, x2, x3 up to, let's say, up to x8. Okay. These are the 8 different values this random variable can take. In this case, if I'm telling you that all the 8 are equally likely, that is, anything can happen at any point, in that case, for each of them probability would be 1 by 8, because total probability should add up to 1. And there are 8 events and I'm telling all are equally likely. Anything can happen. The probability of any of these happening, x1, x2, x3, whatever, is equal. In that case, probability of all those will be 1 by 8 each. So how do you find the entropy, h of x, or entropy of x? How do you find this? This is equal to, you have to do this minus of summation of over each value of x, probability of x into log p of x, which would look like minus of, what is the probability of x? 1 by 8, and log p of x, log to the base 2 1 by 8. Again, for each of the x, you have to do the same thing, minus 1 by 8 log to the base 2 1 by 8 minus 1 by 8. This you have to do 8 times. So instead what I can do, I can write 8 into this. So I would write 8 into 1 by 8 log 1 by 8. Okay. And minus 8 into 1 by 8. This would be 1. So this would be minus 1 into log to the base 2 1 by 8. And what is 1 by 8? 1 by 8 can be written as 2 power minus 3, right? 1 by 8 is equal to 1 by 2 power 3, which is 2 power minus 3. This can be written as 2 power minus 3. So this is log 2 power minus 3 to the base 2. So I can take this minus 3 outside, then it would be minus 1 into minus 3 into log 2 to the base 2. What is log 2 to the base 2? It is 1. So this would go off, which would mean answer is 3. 3 bits. See, entropy is measured in bits. That is, when it is in log to the base 2, it is measured in bits. We'll talk about the other later. So 3 bits are required in order to transmit the information. So what does this mean? Average bits that are required in order to transmit this information is 3. How can you understand it? If you have 8 different possibilities and all are equally likely, how can you use 3 bits in order to transmit this information? These x1, x2, x3 up to x8, they can be represented each using 3 bits. How can it be? It can be like 0, 0, 0 can be x1, 0, 0, 1 can be x2, right? 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. These can be 8 different bit encodings which can be used to represent x1, x2, x3 up to x8. So here you understood, when entropy is 3 bits, that means minimum you will require at least 3 bits in order to transfer this information. That is, you cannot do this in 2 bits. Minimum you will need 3 bits at least. That is the thing, considering that all are equally likely. Now I'll tell you some extra information and then we'll see mathematically how it is. I'm telling you that if the events are not equally likely, in that case, the number of bits required would decrease. Why will it decrease? Because entropy, we told that in case of entropy, I'll write h of x only. In case of entropy, we told that if the event is highly probable, that is, you already know this is supposed to happen, then the entropy would be lesser. And if it is very improbable, that is, you never expect this to happen, then entropy would be higher, right? Here, when all are equally likely, probability of each of those is 1 by 8, which means less than 20% is the probability of each of the event occurring. Which means all of the occurrences, be it x1, x2, x3, whatever it be, all of those are improbable, which means all of them contain good amount of information. Which means in total, there is a lot of information for you, But the same case, if there are some events which are highly probable, let's say x1, x2, x3, these 3 are very highly probable and the remaining are very less probable. In that case, the probability of some events would be, let's say, 30%, 40% and so on. Which means on these events you get less information. Plus, an added thing is that most of the occurrences that would happen will be of these events only, because these are highly probable. Because these events are highly probable, most of the occurrences will be of these events, and these events would have less information. So in total, if the distribution of probability is not equal, that is, if they are not equally likely events, then the entropy would go even lesser, which means if 8 different values of x, the random variable x, were not equally likely, then you can express it in lesser than 3 bits. Do you want to know how? Let's see. See, let us consider that these are not equally likely. In case these are not equally likely, let us say this x1, x2, x3 up to x8, they take probabilities like this. Let's say x1 is of probability 1 by 2, which means 50% of the times x1 occurs. Let's say x2 is of probability 1 by 4, which means after x1, from the remaining half of the occurrences are of x2. And then x3 is of probability 1 by 8, x4 is of 1 by 16, and let us say the remaining 4 are all of probability 1 by 64. Okay, so the 8 different values that x can take, they are of probability 1 by 2, 1 by 4, 1 by 8, 1 by 16, and the remaining are all of 1 by 64. Let us find entropy and understand. Entropy h of x. This is equal to minus 1 by 2 log 1 by 2, right? Minus 1 by 4 log 1 by 4, minus 1 by 8 log 1 by 8, minus 1 by 16 log 1 by 16, minus, there are 4 times 1 by 64 log 1 by 64. So I'll write 4 times 1 by 64 log 1 by 64. And remember, all these log are in base 2. I didn't mention, but I didn't write specifically, but all of these are base 2. So here 1 by 2 I can express as 2 power minus 1. 1 by 4 I can express as 2 power minus 2. 1 by 8 can be expressed as 2 power minus 3. 1 by 16 can be expressed as 2 power minus 4. And 1 by 64 can be expressed as 2 power minus 6, right? And this 4 and 64, I can cut this off. It can be 1 by 16. Okay. Then if I take all these minus outside, then this minus 1 would come out. Then it will be minus 1 into log 2. What is minus 1 into log 2? Minus 1 only, because log 2 is 1. So this I can write as minus 1. This would be minus 1. This would be minus 2. This would be minus 3. This would be minus 4. Log would go off. And this would be minus 6. Minus 4. So now I can cut 2 minus, 1 minus and the other minus would combine to become plus, which means minus 1 by 2 into minus 1 is 1 by 2. Minus 1 by 4 into minus 2 is again 1 by 2. So this can be written as plus 1 by 2. Minus 1 by 8 minus 3 can be written as plus 3 by 8. Minus 1 by 16 minus 4. This can be written as plus 4 by 16, right? And minus 1 by 16 minus 6. This can be written as plus 6 by 16. Okay, so I am rubbing these off. So this, okay, 4 by 16, this can be 1 by 4. So now 1 by 2 plus 1 by 2 is 1 plus 3 by 8 plus 1 by 4 plus 6 by 16. This is what you have. So how can you write this? You can take all these 3 you can take to the base 16, which means this would become 6 by 16. This would become 4 by 16. This would become 6 by 16, which is 1 plus 16 by 16. That is 1 plus 1, which is equal to 2. This means you need only 2 bits to transfer this. Previously we saw that if there were 8 different values the random variable can take, which were all equally likely, there you needed 3 bits, which entropy was 3, which means at minimum you would need 3 bits if you want to transfer that information. Instead, if they are not equally likely, in that case we have seen that if these are the probabilities, then you need only 2 bits to transfer. How can you transfer this with 2 bits? Let's see. You would be thinking, how is it possible with 2 bits? The reason is, first event, in order to show this, we'll use only 1 bit. That is, x1 will be represented as 0. What about x2? x2 will be represented as 1 0 and x3 as 1 1 0, x4 1 1 1 0. Now the beauty is this will happen 50% of the times, which means 50% of the times you need only 1 bit to transfer the whole information. That is the point in entropy. That is, you don't need a lot of bits because in total you need 2 bits in average. The reason you need only 2 bits in average is not because every single x can be represented in 2 bits, but it is because the most frequently occurring value of x, that needs only 1 bit now, and that is occurring 50% of the times. It has a probability of 1 by 2, which means 50% of the time you need only 1 bit to transfer the message, and during the remaining times you need 2 bits, 3 bits, 4 bits, and there are 4 occurrences which are of very less probability. 1 by 64 means out of every 64 occurrence only 1 time it will occur. So for representing those you can take more bits. So you will do 1 1 1 1 and then 0 0, then 1 1 1 1 0 1 1 1 1 1 1 0 and 1 1 1 1 1 1. This would be the 4 representation for these 4 very low priority events. So even if you use 6 bits there, still it won't add up much because you need to use this only 1 out of 64 times. That is the thing, right? So this is how entropy is lesser. So what you have to understand in total is entropy will be maximum, highest if all are equally likely. That is, if there are n different possibilities, then if the probability of each of those is 1 by n, in that case entropy will be the highest. If they are less probable or it is not equally likely, then entropy will go up. Entropy is the information content, which can also be understood as minimum number of bits that are required to transmit.